So as you prepare to watch this video, I'd like you to get two things. First, get your calculator. And then second, well, this is optional. The second thing is go ahead and get yourself a cup of coffee. And think about what happens as you pour that steaming hot cup of coffee into your cup. It doesn't stay steaming hot for a long time. It actually tends to cool at a certain rate. And that rate is actually proportional to the temperature difference between the cup of coffee itself and the surrounding environment. Essentially, that cup of coffee obeys what's known as Newton's law of cooling. And Newton's law of cooling is connected to calculus and differential equations. And so for this video here, I have an example involving a cup of coffee and how it actually can be connected to Newton's law. So let me just open up right now by telling you what Newton's law of cooling actually is. It's written here at the top of your paper or on the screen in front of you. Newton's law says this: the rate at which an object cools is proportional to the temperature difference between the object and its environment. Now, in our example today, it says that our initial temperature of the cup of coffee is poured at a temperature of 190 degrees Fahrenheit. And of course, as that cup cools, it's going to obey Newton's law. So let's see how this can connect to a differential equation. Well, the rate, there's that word rate, so that's, again, our dy dx, that's going to be the differential equation. The rate at which an object cools is proportional. Is means equals in mathematics. That word proportional basically just means we need to think about putting a constant of proportionality in this equation. So we're going to call that k. So k times proportional to what? Well, the temperature difference between the object itself and its environment. So we'll just say capital T for temperature minus the environment, or the temperature of the environment. So there's kind of the rundown on how Newton's law of cooling works. Part A says to write a differential equation expressing Newton's law. And we're going to use some variables here. T for temperature of the coffee. Lowercase n will represent the number of minutes that have passed as the coffee cools. And then I'm going to cross out this letter C here on my paper and call it capital E. Let's let capital E represent the temperature of the environment. So here we go. The dependent variable would be the temperature. Time is n. So dt dn is the differential equation, and that equals k times capital T minus E. It varies directly in proportion with the difference between the temperature of the object and the environment. Now we know in this example, let's actually move ahead here, and there it is, part B. Assume the room temperature is a constant 65 degrees. So I can come back here and just make one little adjustment on this differential equation. We'll call that dt dn equals k times T minus 65. We'll go with a 65 degree room temperature for now. All right, so let's see here. We're going to go separate. So 1 over T minus 65 dt equals k times dn. Separate those variables. Put the capital T's on the left, and we'll put the n's on the right. Separate and now integrate. So I will have the log of T minus 65 equals k times n plus c. K is a constant, so its antiderivative with respect to n is just going to be k times n. All right, now we're going to try to solve for t. Let's see what happens here. If I exponentiate both sides, well, I'll have T minus 65 equals e to the power of kn plus c, or that's the same thing as saying c e to the power of kn. And if I use plus or minus on the c right there, I can get rid of the absolute value bars. I'm actually going to do 2 steps in one. I'll add the 65 over as well. Plus or minus c e to the k times n. So there would be a general solution to that differential equation involving the coffee. But the question up here has a couple initial conditions for us here. It says assuming that the room temperature is a constant 65, and then after 2 minutes, the coffee has cooled to a temperature of 160 degrees. So 2, 160, I'm going to use in a little bit, but the first condition up here is that right away, when that coffee is poured, it is a temperature of 190 degrees. So 0, 190 is the ordered pair that I'll use to solve for the constant of integration, not the constant of proportionality, that's K. We'll get to that in a minute. So here we go, plug in 190 for T. 190 equals 65 plus or minus C e to the power of K times N, but N is going to be 0. So e to the 0 will end up being 1. So now I have, let's subtract 65 actually, 125 equals plus or minus C times 1. And the issue now is which is it? Is it the plus or the minus? C is going to be 125, or is it negative 125? Let's figure this out here. When I plug in a 0, I want to make sure that the output is 190. Well, that's only going to happen if I look back over here at my equation for T. Plugging in a 0 there for N will only happen if C is a positive 125. So I want the positive root here. T equals 65 plus my C value, and then e to the power of K times N. Almost done. Moving on over, there's one other initial condition, and that is at 2 minutes, the temperature has cooled to 160. So now I can plug in a 2, I can plug in a 160, and I can solve for K. Let's do it. 160 equals 65 plus 125 e to the power of K times N, and equals 2. Subtract 65. And let's divide by 125. Check with your calculators. 0.76, I believe, is what that comes out to be. And let's switch forms here. So let's take the log of both sides. Log of 0.76 will equal my exponent of 2k. So here's my k value, the constant of proportionality. The log of 0.76 all over 2, which is approximately equal to, divide that out on your calculator, and we should have a negative 0.137218. There's the decimal solution for K. So I've solved for K, I've solved for C, I'm now ready to write my equation. In fact, let's put that right down here in part C on my paper. T of N is equal to 65 plus 125 e to the power of negative 0.137218, and then n. So there's my particular solution, function t, written all in terms of n. Now, a couple little extension questions here. Letter C says to explain its parameters. Well, notice that the k value is negative. If the k value is negative, that's the constant of proportionality, we're dealing with exponential decay. And that should make sense because we know that the temperature of the coffee is decreasing over time. It's going to be cooling, so it doesn't stay at 190. It doesn't get hotter than 190. It actually lowers, the temperature lowers and decreases according to Newton's law. So sketch the graph. If you want to graph that on your calculator, we have an initial y-intercept here of 0, 190, and then we have this sort of decay function that's happening as time passes. But notice that the temperature doesn't just decay down to 0 or below 0 temperatures. The coffee's not going to freeze. Well, at least inside this room that has an ambient temperature of 65 degrees. And that's where this next question comes into play. Find the limit as n approaches infinity of t. Well, think about this. The limit as n approaches infinity of my function t would basically mean that this term with the e to the power of negative 0.137 times infinity, that's all essentially approaching 0, and then I have a plus 65 on the end. So really that limit is just going to be approaching 65 degrees. This is the horizontal asymptote. T equals 65. Graphically, y equals 65. The coffee is not going to cool any cooler than the surrounding air temperature in the environment. So there's your limit and the asymptote. And then finally, I'll end with this question here. Letter D says, when does the temperature reach 95 degrees? So I can just go back to my equation, which again was T of n equals 65 plus 125 e to the power of negative 0.137 times n. So I can plug in 95 for t, and we'll solve for n. Let's see here, subtract 65, we'll get a 30, and then I'll divide by 125, so 30 over 125 equals e to the power of negative 0.137 n, and then finally log of both sides. And then I can find a solution for n, just divide both sides by that decimal number there of negative 0.137218, and n should be approximately equal to, check that on your calculators, 10.4 minutes or 10.417 minutes, depending on kind of where you rounded your decimal answer solution. All right, there we go. So I hope that was enough time for you to not only learn something about Newton's law of cooling, but also enough time to enjoy a very nice cup of coffee.